Okay, let's start. Welcome to everyone to this webinar. It's a technical webinar about how to solve the PBF, it's the powder bed fusion, laser beam in metal challenges that are in industry. It's a webinar organized by the Custodian Consortium. And after more than 3 years, as we will explain, have been working in developing a new methodology in order to solve some challenges to the automotive, the aeronautics, the aerospace industry. And in this project, what we have been doing is making different researches with different processes in order to achieve better efficiency and cost in this kind of processes. The Custodian project has received funding from the Horizon 2020 program, and the partners of these projects are IMEN, K-Labs, Politecnico di Milano, SECFO, IDIME, GFM, Presitec, Marelli, NIT, and Tuvien. During this webinar that will take more or less 1.5 hours, we will make an introduction about the results got at the Custodian project. Then it will be made by IMEN. Then K-Labs will present the MPLC technology and how it works. After that, we will have Polimi and IDIME who will talk about the PBF of nickel alloys and the metallurgical issues behind. Then we'll have a simulation or the explanation about the comparisons between the simulation and the real application from Tuvien. And finally, IDIME will explain the application of the beam shaping to the PBF of nickel alloys. Last but not least, the inline control system that has been used in the project will be explained by IMEN and NIT. And finally, the Q&A, because during the different presentations, all the doubts and questions that you have can be left in the chat, and at the end, in the final slot, we will read them for the speakers to respond, to answer all the questions that you have. Thank you on my side. My last comments is that you can, if you want to know more about the Custodian project, you can visit shapeyourlaser.eu, and there is a website where we publish all the results from this project. And as I said, you can introduce questions, doubts, and use the chat, please. Well, at the end, we will have this interesting Q&A session. We expect all from your side. And that's it from my side. Thank you to you all. And let's go with the first presentation from IMEN. It's Daniel Gesto, who will make an introduction about the Custodian project.
Hi all. Good afternoon all. Thanks for joining us today in this second Custodian webinar, this time focused on PBF. Let me share my desktop and my PPT. Please confirm, Sergio, that you can see my slides, even
yes,
though they are not still in. Yes. They should be appear now in presentation.
Perfect. Yeah, it's okay.
Okay. Well, thank you. Let me introduce myself before moving on the technical part. I'm Daniel Gesto, so I'm working at IMEN Technology Center in Spain. I'm the project manager of Custodian. So today I'm going to make a short introduction about the methodology that we have developed during this almost last 4 years. And this technology based on MPLC technology has been developed in order to solve some industrial laser challenges that cannot be solved by using conventional systems. And in this I will tell you something later on about the nickel alloys. Well, here you have a brief outline of my presentation. First of all, I will make a very short introduction about beam shaping and different alternatives that we have today, either in the market or still under development, or to get to beam shaping. Then I will provide you some general information and some words about the methodology that we have developed during custodian. And finally, I will just introduce the application use cases we have been working with during this last 4 years. And particularly, I will pay more attention this time to PBF. Well, here you can see different beam shaping approaches that, as I mentioned before, are currently available in the market or even under development. Some of them are relatively new. So here you can find the one from C-band, which is combining coherent beam combined with optical phase array. Other techniques like diffractive optical elements, adjustable rim mode, spatial light modulator, performable mirrors, refractive optical elements. There is a lot of information now on the internet about that. Each technology has its own features and regarding different characteristics. So like shaping complexity, power handling, price, efficiency, the possibility of coupling these systems with existing equipment, and so on. There are some advantages and disadvantages in each of them. And today we also have a new technology that has been developed by our partner K-Labs, French partner K-Labs, which is called multiplane light conversion. This technology was initially used in communications, but nowadays it's being applied to have specific beam shaping. What this technology can provide is a freeform beam shaping through succession of spatial phase profiles and propagation. I will not be interested in details in this technology, since our partner K-Labs will provide you more details about it later on in the following talk. But we think that this technology is being an excellent candidate, particularly for high power, and obviously is totally compatible with current power sources. So you don't need to buy a new one. There are some steps before, but this is one of the main advantages, I think, in this technology. Well, let me now give you some general data about Custodian. Custodian was funded in the called ICT H2020 program in 2018, particularly in the topic ICT4. This project has approximately almost 5 million euros of budget, and the consortium is composed by 10 partners from 5 different European countries. The initial duration of the project was 3 years, but due to different reasons, the duration was finally 45 months. Starting the project in December 2018, and this month the project is finishing. And here, what you can see is the general scheme of the methodology we have developed during these last 4 years. Let me say a few words about it. As you can see here, we have different steps covering this methodology. The first one, and one of the most important ones, is first of all, the analysis of the process and the material in order to define the optimal thermal cycle in order to solve possible challenges in the industry. For example, in the case we are presenting today is how to manufacture by powder bed fusion a component based on nickel alloys, avoiding cracks. So the first thing we have done is to analyze both the process and material in order to define the desired temperature or thermal cycle or temperature profile. Then in a second step, what we have done is to dedicate a lot of effort to laser process simulation, and in order to define the most promising beam shapes to achieve this desired temperature profile we have defined before. There is obviously a third step based on the manufacturing of this beam shape by using the MPLC technology developed by K-Labs. And of course, we have another final step about integration and testing, this time in IDIME facilities. And we have an additional step that has been related to the inline control system based on a specific sensor developed by NIT, or in the medium spectrum of infrared. Okay. Then just to introduce a little bit the three main use cases in which we have been working during these last years. First of all is LBW. We already organized a specific webinar for that. The idea was to increase productivity and robustness in stainless steel welding for exhaust system components, in which we have very good results by using this technology. The idea was to cover different gaps or variable gap along the joint during the process. So we were able to maintain quality during the process, even though we have different gaps in every component. Of course, we have the PBF solution. I will provide you more details in the following slide. And finally, we also added during the project, because it was not included at the beginning, specific case in cutting, laser cutting, in order to increase quality and productivity of the cutting processing steel, particularly stainless steel. So just to present you very briefly, because my colleagues from IDIME will talk about later on. But well, the idea here in PBF was to demonstrate the fabricability by this process of PBF of nickel-based challenging components. These components are quite susceptible to form cracks. So as I presented before, what we have done is to study first the thermodynamics and all in order to define the thermal cycle. Then with our colleagues from K-Labs and 2BN, by using simulation, we define the optimal or most promising beam shapes. Then K-Labs manufacture this MPLC system that you can see on the right, on the left-hand side, already installed in IDIME. And finally, we did some tests that Mario are going to present later on. So, well, that's all from my side. I think as an introduction is more than sufficient. So thanks for your attention, and I will leave you with my colleagues and with, for sure, more interesting and deeper presentations. Thanks.
Okay, thank you, Daniel. Thank you very much for this clear introduction. And now let's go with Gwen Pallier from K-Labs, who will make a clear explanation about the multi-plane light conversion technology that they have developed. And Gwen, the floor is yours.
Hi, hello everyone. I'm really glad to be here with you for this webinar about the Custodian Consortium. So my name is Gwen. I'm working at K-Labs. We are in charge of the development of the beam shaping systems for the Custodian project. Unfortunately, I cannot be here in live with you today, so I have recorded this video, but feel free to contact me if you have any question after the webinar at gwen@klabs.com, or to contact any of the consortium members. They will redirect your question to me. So this time we will focus on the technical aspect of the beam shaper development for one specific application, powder bed fusion with laser beam on metal, so additive manufacturing. Let me please start with a few words about K-Labs. K-Labs, we are a company based in France, in the west of France, and we are actually developing, manufacturing, and selling innovative optical components. What does that mean exactly? Well, we are developing beam shapers from the conception to the cell in REN based on a unique technology, which is called MPLC, for multiplane light conversion. I will explain the MPLC later on. So all this has been developed by our CEO during his PhD more than 10 years ago, and it's been patented from the beginning of the company. We are working with partners worldwide, and there are more than 50 people now in the company, and we are actually now entering very new, nice, and big buildings that we will be happy to welcome you in. So this technology for beam shaping can actually be applied to a lot of different applications. It can be applied to telecommunication application, for example, the local network improvement, or space communication, communication between the ground and satellite. It can also be applied to medical or to defense. But today we are here to discuss about laser material processing. So whenever a laser is used to manufacture any part, it can be a watch, a TV, a car, a plane, there is a step of the process where it's hit by a laser. And that step, this is where every time we want to try to improve it. Either we want to improve the yield of the manufacturing step, either we want to improve the quality. And we are doing that thanks to MPLC. So how does an MPLC work? Well, actually, there are a lot of ways to shape light. Some technology are based, for example, on diffraction. So you will use some specific laws of optics, the laws of diffraction, in order to make the shape you need at the place you need it. You can also do it with very different laws. The laws of Fresnel, for example, it's just a normal, the classical ray tracing laws. This is what is used, for example, to design, microscope objective, for example. And K-Labs, we are using all the laws. We are using the mode propagation of the laser. So we will characterize very properly all the modes of the laser, and we will propagate them one by one. And doing that, we will really think the light propagation very differently. Now this light, which is propagated with all these modes inside it, it's actually getting through a lot of different phase plates. Multiple phase plates can be really very big numbers or a quite small number. What is very important is that you have to have propagation in between the phase plates. So this actually leads us to have the capability to do any kind of shaping. We can do simple shape, but we can also do very complex shape, like asymmetric shape or shape made of two subshapes, which are far one from the other. What is also very important to understand is that thanks to all these phase plates, we can actually control not only the intensity profile, but we can control also the phase profile. So it enables us to have a plano phase where we have our shaped beam, which means that we will have a pretty nice propagation of this shaped beam, meaning that you have your top hat somewhere, you have the same top hat before and the same top hat after. This is generally not the case with other technology of beam shaping. As you can see, most of the time, this is actually fully passive. So we have no intrinsic loss due to the way we do the calculation. And actually along the way, we realized that the transmissive way that is described on the left image was not so convenient. So we have decided to make it in a reflective way. So now we have the light, which is going back and forward, two mirrors. One of them is textured with a faceplate on it. The other one is just a standard mirror. I will show you a video about that in just a minute. So what is also very important to see is that you can have multiple beam at the input that you will combine, for example, inside another output, or you can have one beam at the input and multiple beam at the output. One also very important point is that the MPLC is working in a fibered environment, or it can also work in a free space environment. So the image on the middle is a classical MPLC that was developed for telecommunication application. So it's definitely not close to what we will be discussing within the Castigen project. So let's now have a look at a short video about MPLC. So this is a faceplate. So you have the light which is going through the different faceplates, 5 in that case, and it's shaping the light from point to ring. You can have actually multiple faceplates, a lot of them. And in that case, for example, it's combining different inputs. And after all the faceplates, each of the systems is combined specially and is also providing a different shape. So it means that, for example, if you couple it in another fiber, they will address different modes of the solid fiber, and that will enable it to not mix one with the other. So it's again a telecommunication application. So the reflective implementation, so you can see you have this mirror, which is textured. In that example, it's 18 millimeter, and you have all the beams which are getting in. So in that case, it's fibered, it's monomode fiber at the input, and multimode fiber at the output. So it's combining all those modes from the different fibers into the different possible modes of the multimode fiber. So it's a multipass scaling. So this example is for telecommunication, of course, again. So you can see that you can have four different modes, different images. And can be inside a box, and that is again it's for telecommunication. But let's get now to how it looks like in our cases. So we will be focusing, as I said, on laser material processing application. This world is actually divided into the world of the pulsed laser applications and the world of the high power CW applications. So that's what we call generally microprocessing and macroprocessing. We will be actually focusing on macroprocessing within the Custodian project, as actually laser cutting, laser welding, and PBF are all done with CW lasers. Our system for microprocessing are pretty different from all the other systems which are based on MPLC. Why that? Well, you actually have to handle really a lot of power. So if you have this one mirror with all the faceplates, then the beam will hit it multiple times, and at the end, this mirror will have to handle really a lot of heat. So it's not so good in terms of heat management. So we have decided that we will have the faceplate on different mirrors, and actually the propagation in between them is actually pretty bigger. So in that case, the distance is actually based on the laser itself. So it has to be pretty big. And we put it inside a laser head because that's what actually has to be done if you want to be integrated on a robot arm. So it's in the case of laser beam welding, it's just an example. So here you have a system which is available for sale as a standard product. So you have the laser, which is coming in with a standard LLKD connector. Then you have a collimation mirror. Then you have 3 shipping wheel mirrors, one after the other. This is the MPLC. And you have a collimation optics with a standard cross-jet, all that from Prestec actually for the external elements. So it's integrated on the robot arm with the MPLC being splitted onto different mirrors, which are all cooled by the back, as you can see in that case. It's not needing any alignment, and it's compatible with standard equipment like a true disc laser, 16 kilowatts. Just shortly, the performance of this system, well, it's actually capable of handling up to 16 kilowatt. Transmission is very good, more than 99%. And since we have this very nice cooling of the optics by the back, it's really optimal in terms of heat management, and it's extremely stable. So it leads us to have, even at very high power, a very reduced focus shift. It's actually very good for a lot of different processes. Okay, so now that we have seen what is MPLC, we have seen what is MPLC for macroprocessing, let's focus on the PBF case. So after all the calculation made by our partners, we have decided to develop the system within the consortium for PBF based on this shape that you can see. It's made of a primary beam, which will be actually Gaussian. This is really an intense Gaussian beam to do all the melting of the powder. And then you have a larger top at the back, which will be made for handling the thermal gradient during the process. So how have we developed that? Well, actually, the idea is to have a dynamic system in order to have live control over the process. But what parameters should be dynamic? This is a very big and very broad question. Actually, with MPLC, it would be possible to have a lot of parameters being dynamic. It can be the shape of the beam. It could be, for example, more round or more elliptical. It can be its size, one beam to the other, the power ratio. But it's actually extremely complex to have a system which is doing all this at the same time. So we have decided to develop, at the first step, static beam shapers with a lot of different parameters. And with these systems, we will validate which parameters are the more important in order to design at the end a system dynamic with just a minimum of parameters which are dynamic in order to have a system which is pretty small with very good transmission and compatible with industry needs, actually. So what were the static system that we have developed? Well, we have decided to actually develop 6 of them with different parameters. So first of all, we have tried 2 different primary beam diameter. One was 180 micron diameter, the other one was 530 micron diameter. So that was for the primary beam diameter. At the same time, we wanted to try different size of the secondary beam. So we have tried 3 mm, 4 mm, and 5 mm diameter with both combination of the primary dimension. At last, we also wanted to try different power ratios. So we have managed to tune the power within one of the shape relatively to the other in order to see what is needed in each case for the melting and for the management of the thermal gradient. So this way of actually investigating an issue is now very standard at Skylab. So we are applying that to other applications as well, and it's actually working really fine. So how did the system look like? So actually, our partners will be describing in details the integration within the machine. Just to be quick on that, actually this machine is very specific because it has to work with f-theta lens and a scanner, and you have to really manage the beam propagation within those systems without damaging the system, which is actually a huge challenge. But thanks to all our tools for simulation, we have managed to tackle that challenge. So here you see that you have the machine, and then pretty far from the machine, actually, after a beam relay tube, you will have our MPLC module doing the shaping and some standard components for the injection of the laser inside the shaping system. Here you have just the mechanical drawing if you want to have a quick look on what was developed. And let's now focus on what result we got with the static systems. I will not get into the details of all the configurations, it's pointless, but you can have a look at one of them, the number 5. Well, actually, the primary beam was really close in terms of diameter compared to what was targeted, because what I described just a minute ago was the target parameters. The secondary beam was actually also very close to the diameter that we were targeting in that case, and we managed to have a very good energy ratio in between both shapes. So the transmission of the system was pretty good, more than 90%. So you can see also that the other static system were actually managing the needs of changing the dimension of the secondary beam to try different options. Now that we have tried all the system, what we will develop in terms of dynamic system? Well, we have decided to actually focus on one configuration of the shape and to manage the pole ratio in between both shapes. So this is just an example of the system on that picture when the integration was actually ongoing. So here you can see the system integrated within the machine, but my colleagues will be describing that more in details after my presentation. And just want to see that actually we managed to have the energy ratio, which is tuned from the expected maximum ratio, 40 to 60%, to the minimum ratio, 20 to 80%, in between the first and the second shape. How you can see that, the image on the right just there, you can see the enclosed energy. So you will see that for example, the first tape is actually roughly, I mean, it's pretty small, and you can see that for the same radius, actually, you have much more power. For example, in 200 micron radius, you have much more power on the top compared to the bottom, meaning that you have actually much more energy inside the primary beam compared to the energy in the secondary beam. So we were very happy that we can actually tune this power ratio pretty nicely in between the targeted range. And now I guess that the most exciting is coming, and you will have the description of the integration of the system and all the process results that were obtained with our partners. So I want to thank you very much for your time. I was really glad to present our custodian results today with you. Don't hesitate to contact me one more time at gwen@skylabs.com, Gwen, Gwen. I would be really happy to answer any question you would have. And I wish you a very nice end of this technical webinar. Bye-bye.
Thank you. A big thanks to Gwen for this presentation about well, how the MPLC technology works. It's part of the heart of this project, and I think it was really interesting to see how she explained the development and the results from this technology. And now let's go to the next presentation. It will be combined. It will be made between Polimi and IDIME, talking about the PBF of nickel alloys, talking about the metallurgical phase or point of view. And first of all, we will have Maurizio Vedani from Polimi, who will start with his presentation, and it will be continued by Mario Martinez from IDIME. Maurizio, when the floor is yours, when you're available.
Thank you, Sergio. I'm preparing the screen.
Okay.
I'm hoping you can see correctly.
Let's wait 1 second. Perfect.
Let's
okay.
wait here.
Yeah.
Okay. Good afternoon, everybody. My name is Maurizio Vedani. I will be the speaker of the first part of this talk, as Sergio anticipated. I'm with Politecnico di Milano, Department of Mechanical Engineering. The outline of our talk is made up of, let's say, 3 chapters. Mainly, I will be dealing with the first one about the theoretical background and some experimental results when for producing standard powder bed fusion processing of nickel, of the selected nickel-based superalloys using the custodian project. Then we will be moving on the strategies adopted for the advanced processing, and Mario will explain us something more about the different strategies that we adopted, and also including the proposal for the most appropriate scanning strategies. Well, talking about the background about the metallurgy of nickel-based superalloys, and especially focusing on the powder bed fusion processing by laser beam. Well, considering processing of this material, especially from the perspective of the material itself, we can draw some information also from the weldability. So the processing by powder bed fusion is somehow strictly related to the weldability, since powder bed fusion is a kind of small-scale multi-pass welding, and the material is feeling more or less the same welding cycles, the same cycles, and the material which is well weldable is also well processable by PBF and vice versa. So we can draw some information from the weldability information about this material, and this is actually has been done by considering also the plot you can see on the right-hand side of this slide, where we can see a sort of map that in this domain made considering the amount of titanium on the horizontal axis and the amount of aluminum in the material on the vertical axis. The domain is split into 2 fields. On the bottom left corner, we have the weldable materials, and you can read maybe also some materials that are more weldable and more processable by PBF. And on the top right corner, this region here, you can read some materials that are more difficult to be processed by PBF and also to be welded. So all in all, the most diluted, less alloyed nickel-based material are readily weldable, while more highly alloyed, the precipitation strengthening materials are more critical in this sense. And this is also the case for the 2 reference material that has been selected for the custodian investigation, namely the CM247L low carbon alloy and the Inconel 713LC alloys. They are labeled here as red, with red labels, and they are definitely in the difficult to weld region. what is the challenge? What are the challenges when processing by PBF by a laser beam such metals, such alloys? There are a number of issues, a number of defects that can be generated within the material. The most important are the first one that are listed here in this list of 4 concerns. We are talking about solidification cracking in terms of cracks that are formed in the very last stage of solidification when we have a fraction of solids already of around 90% due to the tensile shrinkage stresses. But also of importance, play a very important role, is grain boundary liquefaction cracking, which is not exactly solidification related to solidification mechanism. It takes place in the already solidified material due to the thermal cycles, due to the intense heating which is produced by either the affected zone of the wells or while during the solidification of the following layers in the powder bed fusion process. So these are very important, but also during the further cooling of the material in the fully solid stage, we can face some troubles with the strain aging cracking because of the precipitation of gamma prime and even gamma double prime phases, and also ductility dip cracking. But for us, at the moment, they are less important. Here, as I mentioned before, we made some tests according to a standard powder bed fusion by laser beam process to investigate the genesis of the possible defects and what kind of defects we had to face with our 2 reference alloys. And actually, it was readily confirmed that after solidification, the material where a lot of crack could be formed in the material by a standard process. I want to be clear, by a standard PBF process. The cracks were intergranular in nature, so they run between one crystalline grain and the other, and they could cross several bed pools. These are some, here you can see some reference images for the CM247 LC alloy, while in this slide you can see some similar images of similar cracks for the Incolel 713 LC alloy. So the point was already always the same. What could we learn from that experience, and what from that experimental experience, and from the literature, from the theory? So there are a number of cracking mechanisms that we have to face and to challenge for these alloys that are non-processable by, let's say, in the are classified as non-processable in the literature. And if we put those mechanisms, those cracking mechanisms, on a temperature scale, as you can see here on the right-hand side of the slide, so we can see that the red temperature range refers to the solidification cracking. Then in the very last stage of, or let's say, right after having finished the solidification, we have liquefaction cracking, and then just to recall, we had the strain age cracking and the ductility dip cracking in the solid stage. So we need to somehow to optimize the thermal cycle given provided by the process in order to at least to mitigate the formation of those defects, at least for the most important one, for solidification cracking and for liquefaction cracking, the red one and the blue ones. This can be done, for instance, by tuning the cooling rate, thus in order to remove or reduce the critical phases and the extent of the residual stresses that are generated during solidification. So, what can we do? In theory, the ideal, let's say, thermal cycles that we can design in order to limit or mitigate those defects can be drawn by some consideration. First of all, I need to say that fast cooling rate cannot be avoided in a laser beam process because of the intrinsic power density of the laser. Quite fast cooling rate is there. We cannot avoid that, but we can use some preheating to prevent, or let's say to slow down a little bit the cooling rate and mitigate the hot cracking. And also we can, if we concentrate this preheating, and or if we can reduce the cooling rate, especially during the very last stage of solidification, then we can also limit and mitigate the liquefaction cracking. This is the most important strategy for the rest of the project. And again, an ideal thermal cycle could be given by this black line where we added the time axis on the previous diagram. There's another point which is quite important to mention, is that, and it refers to the fact that I was talking about an ideal single thermal cycle, but in a real process, it's very difficult to think to an ideal thermal cycle because the powder bed fusion process is made up of a high number of different passes. So it induces on the material a number of thermal cycles in the space domain and in the time domain that are very difficult to even to imagine in our mind. That's why we appreciated very much the contribution given by the simulation, which will be considered and explained in a further talk in this webinar. Okay, I can now leave the floor to Mario in order to go ahead with the rest of the presentation and talking about the advanced processing by PBF system.
Thank you, Mauricio. Good evening, everyone. Thank you again for joining us today in this webinar. This is Mario Martinez from IDIME speaking. I'm now introducing the methods and procedures that were used to obtain feedback from the PBF, from the powder bed fusion laser beam melting process, so that the simulation model was adjusted to obtain the custom beams to tackle this hot cracking issue that Mauricio has been explaining right now. So for this purpose, these are three of the tests that we carried out at the very beginning of the project. On the one hand, in order to obtain those thermal cycles, those optimal thermal cycles that Mauricio was describing, and that will help to mitigate this cracking issue in these alloys, during the processing of these alloys, we carried out the preheating of solid blocks and single track remelting of both materials to assess the crack presence and their different cooling ramps and the different cooling thermal cycles. So with these experiments, the main intention was to define certain conditions where the cracking phenomenon was eliminated or mitigated, right? On the other hand, a process parameter optimization was carried out for both materials, for the CM247 low carbon and the Inconel 713 low carbon, with the standard setup. So with no preheating, no custom beams, just with a common Gaussian distribution beam of a standard PBF process, with the aim of finding the processing conditions where these powder alloys can be formed into solid parts with high density and with reduced amount of cracks. And last but not least, we got plenty of process feedback as temperature profiles and the melt pool size, as melt pool depth and width, and we designed the most appropriate design strategies where we can carry out the powder bed fusion experiments. Mauricio, if you can skip to the next slides. So regarding the first test as we did, the study of these thermal cycles required in the process of these alloys, we followed, as you can see, two different approaches with the same purpose, which is to heat up a solid block that you can see on the left side. This block is made of these two alloys, the CM247 and Inconel 713 low carbon, and we heat up these blocks up to a certain temperature. And when this temperature this target temperature is reached, we stop the heating source and we perform a single track on the part. In this way, we are able to modify how the melt pool is solidified, and therefore we can reduce or we can manage how the cooling rates, the cooling rates during the process, let's say. So to do this, we first we designed and integrated a heating device, an induction heating device that you can see on the right side, on the top right side of the screen. It was designed and integrated in the PBF in the powder bed fusion system. However, with this system, we only were able to reach preheating temperatures up to 11 to 1200 degrees C. So for this reason, and as we still observed cracks in those samples, we proposed a novel approach, which is the one on the bottom part, on the right, which is heating the sample with the consecutive laser scan tracks nearby the area of interest. So here you can see an orange hatchet area, which is on top of a gray part, which will be the CM247 or Inconel 713 low carbon sample. And this hatchet area is repeated consecutively until the nickel alloy reaches a certain temperature by conduction. So once this temperature is reached, we stop these hatching repetitions, and then we perform a single track at 2 millimeters, about 2 millimeters far from this area, which was heated as well. So as you can see here, this purple circle was the measuring point where we were measuring the temperature after, before, and during the melting process of the single track. So in this way, we were able to at least to measure at which time temperatures this phenomenon, this cracking phenomenon, is mitigated. Mauricio, if you can skip to the next slides. And here you can see some of the samples that we got using this approach. As you can see on the left side, there is a CM247 low carbon block that was heated up to 900 degrees C. And the CEM cross-section images that you can see, well, we can observe cracks that starts in the weld metal zone and extend into the heated affected zone. However, if we look at the samples shown on the right side, they correspond to CM247 low carbon as well, but in this case the sample was heated up to around 1330 degrees C. We can clearly see that the cracks are not present. Thus, we can conclude that that very high temperatures must be achieved if we want to get rid of cracks. And Mauricio, if you pass to the next slide, same behavior for Inconel 713 was observed. So in this case, the cracking phenomenon is less evident, maybe in the sample heated up to 900 degrees C. But still, we still see these small cracks that you can see on the bottom image on the left. However, and the same behavior and the CM, if we heat the sample up to 1330 degrees C, about, we cannot observe those cracks that were present at lower temperatures. So, well, in order to get feedback about which conditions are required for processing these two nickel alloys, we mapped the processing window for both alloys with the standard beam, with the Gaussian distribution beam, just to make sure that we can produce parts using very similar conditions and to give some feedback to the simulation as well. So we could conclude that an energy density, a volume energy density of 120 joules per square millimeter was required, and that both alloys can be processed under very similar conditions, because in the end, as Mauricio presented, both of them present very similar chemical composition, right? Mauricio, can you skip to the next slides? And as mentioned before, prior to the beam shaper definition, some tests were conducted in order to obtain some process feedback and some information to support to the simulation model, right? So as we are modifying the shape, different approaches were initially proposed, as you can see in the table. However, as you may know, powder bed fusion laser beam melting process works very random, and it works producing tracks in multiple directions, moving back and forth continuously. We have to bear in mind that asymmetrical shapes might affect negatively the samples because we cannot rotate the shape with the MPLC. So several tests were conducted, were carried out under different scanning conditions, as you can see on the right side of the slide. And we concluded that bidirectional scan tracks and rotation between layers is mandatory. Otherwise, we can observe that the cracking issue is even worse, and we observe this swelling and this irregular top surface on the part. So that's the reason why we went for a round symmetrical shape, and the one that was proposed for the MPLC. And last, Mauricio, next slides. As I was saying before, some information about the process was acquired and was studied to feedback to the simulation model to adjust these thermal cycles on the simulation model. And for instance, this is one of the tests that we did for CM247 low carbon. So basically here we added layer by layer, we added powder layer by layer, and in the last layer we added a powder bed again, but we just melted a single track. And the reason for this experiment was to measure what was the weld depth and weld track, the dimensions and the geometry of the track, so that it can be replicated by the simulation, right? And that's all from my side. Thank you. If you have any question, as Sergio said, you can drop the question in the chat box and we'll be happy to help you. Thank you.
Okay, thank you to you all, Mauricio and Mario. Very interesting how both explain each part of these experiments and the tests that you made. And let's go now with a presentation of the simulations. It comes from Tuvien. It will be Konstantin Sens who will explain well how a simulation-based process optimization of the PBF LBM and the results he obtained. Konstantin?
Thank you. I will quickly share my screen. So I hope you see now the presentation in full screen mode.
Yeah, perfect.
Perfect. So welcome, everybody. My name is Konstantin Sens. I work at TU Wien in the research group of photonic technologies. And I will be talking a little bit about the simulations that we performed during the custodian project. So in the beginning, I will quickly give an overview about the physical phenomena involved in PBF LBM and how we can mathematically model these phenomena so that we can perform simulations of the real process and therefore have some kind of a computational experiment where we can try out different things and see how different laser parameters, for example, affect the outcome of the process. We'll also show some example of those simulations that you can get a better understanding what conclusions can be drawn from such simulations. Then I will be talking about the beam shaping methodology and how we defined optimization criteria based on the metallurgical insights that we just heard about in the previous presentation. And yes, and finally, I will also talk a little bit about multi-layer simulations. So let's dive right into it. So in any laser material processing or process, it's always very similar. It doesn't really matter if it's welding or additive manufacturing or cutting. We have some material, which is metal in this case, and we have a laser beam and they interact. And we really want to model the fundamental physics that are happening here. And it's a lot of different phenomena which are coupled. So we of course have a laser beam which is propagating through some medium and then is interacting with the material. We have some absorption and reflection, and then the material is heated and will undergo some phase transformations and so on. So each of the different physical processes is modeled through a set of different equations, which we then solve in a continuum mechanics approach using the open foam environment. And this is an open source code platform which allows us to do our own developments and quickly adjust the simulation tool to include different models and so on. So the fluid flow of the liquid metal and also the vapor, which can be metal vapor or shielding gas. This is, for example, modeled with the Navier-Stokes equations. And we have some free surface of the liquid. And there, of course, there are important forces such as surface tension induced forces, the Marangoni currents, for example, but also some vapor pressure from vaporizing metal. And then the laser beam, which is interacting with the material. We have, of course, some angle dependent and wavelength dependent absorption and reflection modeled through the Fresnel equations. And this amount of energy which is absorbed by the metal is then conducted and convected through the material. So we have to model this energy transport. And of course, the material can undergo phase transitions, so it can melt and solidify or even evaporate and condensate and so on. And then there's, because we're talking about powder bed fusion, there's, of course, the specialty that there is some powder involved. So we also have to, in some way, account for the powder layer. And there is initially, we chose the approach of modeling individual powder particles. So here you can see a simulation where we just try to achieve a realistic powder bed distribution of different sizes and so on by dropping powder particles so that we can accurately model the melting of the powder. And if we use such a powder bed in a simulation, you can see here now how this actually looks. The powder melts when the laser beam travels along and is added to the bulk material. And so layer by layer, we add material. But the problem with such an approach is, of course, I mean, it's really accurate because we really model individual powder particles, but it's also computationally very expensive. And the larger the process is that we want to model, the more prohibitive it gets, especially when we want to do process optimization later on. So what we then did is we developed a continuum mechanics only approach where we do not model the individual powder particles, but we just have an additional phase that has powder-like properties. So the thermal conductivity, the absorptivity of laser energy, or the density and so on represent those of a powder bed, but we do not, but we regard it as a bulk of material. So this is what you can see here now. On the right-hand side, this is an experiment performed by IDEME. And on the left, you can see a corresponding simulation. And now you can see this dark gray area. This is representing the powder. So it has the same thermal conductivity and density and so on like powder, but we do not have to consider individual particles. And then the laser beam melts this powder, and we can actually see some evaporation also going on, and the melt pool, which is forming. Everything that is colored from red to blue, this is liquid material. So we can see also, in this case, in this simulation, you can see, for example, some heat accumulation as the top of the melt pool is of the previous track is always still liquid and not solidified yet. So this is kind of how the simulations look that we performed during the custodian project. This is now, these are multiple tracks. This is about 50 tracks to perform a 5 by 5 millimeter area of processing. So if we continue on, we heard in the previous presentation already that we need to somehow lower the cooling rates in this process within a certain temperature range. So we call this critical temperature range the brittle temperature range, and this is a very high temperature. It's slightly it's in the region of between solidus and liquidus temperature and slightly below the solidus temperature of the material, and it depends obviously on the material. And so within this temperature range, we want to lower the cooling rate. So what we did is in each simulation that we performed, you have a graph on the top right. We measured the cooling rate. So this is just how fast does it cool, Kelvin per second, the volume of material. So we have three plots here, and this is just how much volume is affected by what cooling rate. So you can see this is, for example, 1 million Kelvin per second. And we have here, for comparison, 3 different sizes of a beam. This is just one Gaussian beam. And the green line is a very small beam diameter, and we just increased the beam diameter to some medium and some large size beam diameter. And we can see how the amount of, how the vast part of material is then experiencing lower cooling rates. So by shifting these curves to the left, this means more material is actually affected by lower cooling rates. And so we can quickly compare different configurations. So if you want to, if we have several sets of laser parameters or beam shapes, we benchmark them against each other by comparing these cooling rate plots, because the ultimate goal is to reduce cooling rates in this critical temperature range that we just heard about in the previous talk. And the other thing that we're closely looking at in the simulation is the width to depth ratio of the melt pool. So on the lower left here, you can see these 3 simulations, so just different beam sizes, and we can see how the penetration depth of the substrate, it stays approximately the same, but the width gets larger, and the higher the width to depth ratio, the better in terms of hot cracking. So these are the 2 criteria which we're looking at when we try out different beam shapes to find an optimum. So let's at first look at some at the results for the first material, the CM247LC. So here you can see a comparison of an experiment. This is just a single track of melting with a powder. So a powder layer and then just one single line of melting powder and therefore welding it to the substrate. And we see some measurements from the experiment. And then on the right, you can see the corresponding simulation result. So this was done to somehow validate that the simulation is reproducing the same weld bead geometries like the experiment. And we were confident the results were satisfactory. So we used the simulation to then try out different beam shapes and find an optimum in terms of weld bead shape and cooling rates. As we already saw before, the beam shape that was agreed upon was a one primary beam with a Gaussian power distribution, and then a secondary beam, which is a larger circle with a top hat distribution, with the aim of providing some additional heating for lower the cooling rates and therefore reduce the cracking risk. So this is just a little larger the plot we've already seen before. So comparing different primary beams, but I will talk about this already. And now what we did is we tested different primary beams, different secondary beams in terms of size and also power. Also looked at multi-track simulations, so not only a single track, because in reality we want to process very complex geometries. And then also what we tried is switching between small and large beam shapes from one track to the other. For example, increasing the size of the beam from during successive tracks, or reducing it. And also we looked at different scanning strategies, so meandering approaches, for example, or uni or bidirectional scanning approaches. Then on the bottom you can see just exemplarily the information which is extracted from these different simulations. So we got different cooling rate plots, and you can see so that the further left such a curve is on this scale, the better. This means overall we have lower cooling rates. For example, this green one is quite bad because it's like lots of volume is affected by high cooling rates. And also we looked at the geometry of the weld bead, which is achieved, and looked for a good width to depth ratio, which is also favorable in terms of cracking risk. In this way, we found a frame of optimum parameters. So minimum and maximum values for the primary and secondary beam diameter and power. This is especially interesting when we then look at dynamic capabilities of the MPLC, which range should be covered by the MPLC, and also the best found combination, which is actually quite a large primary beam. And this is, of course, the larger the primary beam gets, the lower the cooling rates will be. But of course, we also have to consider that we want to remain some precision in the machining capabilities. And also, the larger the primary beam becomes, the more power we need to penetrate the substrate. And then we are left with less power for the secondary beam. So there's also a trade-off and then an optimum that was found. And then let's quickly look at the Inconel 713 LC material. Here the optimization looked quite similar, but in the beginning, in the experiment, it was found that there was an issue we've referred to as balling, so that these are results from single track experiments, and you can see that we have an unconnected weld bead of sphere-like structures. And so the substrate wasn't really penetrated well, and the liquid couldn't wet the substrate, and therefore we see these high contact angles in the liquid, and then it solidified and formed these unfavorable cross sections. And we then simulated these exact conditions, and you can see here now a video from such a simulation, and you can see how the power is not high enough to really penetrate the substrate, and then the surface tension will sort of form these sphere-like structures. And then the further this goes on, the heat input is over time, of course, increased, and it gets less, but we still cannot produce sufficiently nice weld bead here. So this so we end up with a similar structure like we saw in the experiment on the previous slide. So this is an issue that is related to surface tension on the liquid surface, which is pulling these spheres together, and a lack of wetting of the underlying substrate. And by increasing the power a little bit, it was possible to achieve a good cross-section and good results both in the experiment and also in the simulation. So after adjusting the power, increasing it, we obtained these results, which you can see here, the experiment, and then again for validation, the simulation result. And after obtaining a good reference in this way, we performed a similar optimization study like for the CM247LC material. And then what we also did is we looked at not only multi-track, but also multi-layer simulations, because in the end, for an industrial process, we also, of course, want to go towards real part production. So you can see here, after each layer where we scan 2 tracks, we add some more powder. And this is also possible within the continuum mechanics approach that we developed here. Here we can see, because the previous melt track, we see some irregularities because of the unidirectional scanning strategy. And then we see that actually the weld speed is too high to be fully covered by the next powder layer. So this is something that could be already seen in a simulation, so that we do not face these problems then in an experiment later. So I hope this was very illustrative for you. And if there's any questions, I'm happy to answer them. Please just write them in the chat. And thank you for your attention.
Okay, thank you, Konstantin. Thank you for the nice simulations. Really, really interesting. And let's go now with the two last presentations. First of them, it's about the application of beam shaping to PBF of nickel alloys. It will be presented by Mario Martinez from IDIME. Mario, when you are available, the floor is yours.
Okay, thank you. Let me know if you see the presentation mode. Moment. Now.
Perfect. Yes.
And you can see the next slides. Now?
Yeah, perfect.
Okay, great. Okay, so good evening, everyone, again, and thank you again for attending the meeting. This is Mario Martinez. I'm working as a research and development engineer at IDIME, and the process at the Advanced Manufacturing Processes Unit. And our role in Custodian project has been to integrate and to test all the beam shaping capacities and control system in the powder bed fusion laser beam melting system. So today I will go through the shapes, so the beam shapes specified within Custodian project. I will do a brief summary of what was mentioned before by Konstantin, and for both for the multi-static beam shaper and for the dynamic beam shaper. Then we will have a quick look at the components that were modified in the powder bed fusion technology. So basically the high power laser, the multi-static and dynamic beam shaper, and the inline process control system as well. And last, I will present you the results obtained from the experimental tests carried out at IDIME, and the conclusions that we can draw from this development. So, as shown in previous presentations, based on the outcome of the simulations carried out by the Technical University of Vienna, we started working with a multi-static MPLC, multi-static beam shaper. This means that we have up to 6 different optics, as you can see in the table on the left side of the screen, that could be substituted in situ to modify the shape. So, as we can see on the table, different primary beams are combined with different secondary beams with the intention of mapping different cooling rates, different conditions, right? Although I will show you later some results, the multi-static beam shaper was substituted by a dynamic beam shaper that was based on one of the configurations, as Gwen explained before, of the multi-static MPLC. So in this case, we are able to modify the power ratio, as you can see on the table, between the primary and the secondary beam by means of modifying the voltage of a piezoelectric, of a galvo mirror. So as you can see here on the table on the right, by changing this voltage, we can obtain different power ratios from about 50-50%, so 50% of the power for the primary beam, 50% for the secondary beam. These are the final measurements that we acquire from the beam characterization, which are slightly different than from the theoretical values. And the last configuration, which gives more power to the secondary beam. So as you can see here, about 23-77% of power ratio. Sorry, in both cases, we are always working, or we are always speaking about a primary beam, which is a Gaussian distribution beam, and the secondary beam of a wide secondary beam with a top hat distribution, right? So the main challenges of the custodian setup in terms of the integration. Let's say, as we are increasing the laser power quite a lot, because our intention is to preheat and post-heat the powder layer while melting, we have to integrate a high power laser, in this case a 4 kilowatt high power laser, and therefore the scanning head was also adapted to this new high power. So new safety protocols and a custom interface was developed for the prototype. I will mention briefly the installation of the static and the dynamic MPLC, which require specific air, water, and a custom interface to make sure that it's working properly. We will speak about the inline control system. I will briefly introduce this because my colleague Roberto will explain later on you. And I would like to show you some additional adaptations that were required in the prototype to make sure that everything works fine. So in these first slides, we will speak about the laser integration. So on the top left images, you can see the previous scanning head that you can see here with those red side panels. This scanning head was substituted by an IntelliScan 13, which is a scanning head that can withstand up to 4 kilowatts. And in this installation, in this scanning head, specific coatings were applied to certain mirrors because we have to make sure that the infrared light was able to come back to the scanning. So this back reflection can be observed by the camera, and so the inline control system can be applied. On the right side, you can see the Concept Laser M3 machine that was used within Custodian project. On the top images, you can see the standard 100 watt laser, which was equipped in this system. And on the bottom image, you can see the high power laser with all the additional devices as the water cooling systems and so on that were installed in our machine. And last, you can imagine that as we have increased the laser power from 100 watts to 4 kilowatts, so something has changed in the security protocols and security measurements. So here you can see some of the installations that we have to do to be in compliance with both the SLM, the PBF machine, and the requirements set by coherent roughing for a high power laser, such as the one that is being used. Regarding the multistatic MPLC, you can see some images here of the installation. Here you can see this multistatic beam shaper was made up of two different modules. One which was installed inside of the machine, as you can see here, and it was directly attached to the scanning head. This module was aimed to perform a fine beam alignment before introducing the beam into the galvo mirrors into the scanning head. On the bottom, you can see the external module, which is the beam shaping module itself. And here you can see the fiber plugged directly into the beam shaper, and here is where the beam is transformed into the desired optic, right, into the shape beams. And as you can imagine, both systems are connected through a shielding tube to make sure that there is not dust, there is not contamination in the system. Otherwise, some damages can be caused to the equipments. And last, I would like to show you some of the lot of modifications that we have to do to the machine so that all of these systems could be installed properly, right? The same for the dynamic beam shaper. Here, I would like to highlight that the alignment module is the same, so no major changes were applied. However, for the beam shaping module, it is completely different, as you can imagine, because now we can control the power ratio by means of software. We don't have to change optics manually. anymore. So this beam shaper is also equipped with a straight line sensor, which is a security measurement introduced by Skylabs, which basically shatter or trigger the laser when it detects a quick change in the light inside of the beam shaper, right? So here, just to add that some water cooling system was installed in the MPLC to cool down the mirrors, and we have to include also an air overpressure to avoid dust and contamination of the system. Here, some of the systems that compose the dynamic beam shaper. This is the power source that allows us to modify this voltage to control the power ratio between the primary and the secondary beam. And last, here is the control inline system. This is the infrared device provided by NEAT and by IMEN, which has the embedded system. And here we have to provide a dedicated air cooling line so that it is in compliance with the cooling requirements of the camera, and a custom interface, because in the end this system is able to modify the laser power in real time, layer by layer, depending on what is happening on the melt pool. So as you can see here, the camera is attached to a camera adapter, which is this one, and here we can find a steering mirrors that where the infrared light comes back to the camera so that it can be analyzed and processed. And here some other additional installations that we have to do, a custom air knife to prevent the dust and the contamination come to the F-theta lens, and the nitrogen dedicated installation to cool down the scanning head cooling, to cool down the scanning head galvo mirrors, because the damage threshold affects when you change from one shape to the other. So we found plenty of issues here, but hopefully we were able to sort them out. So I will now move to the experimental testing, and first we will see some very brief slices of the multistatic, and then we will go to the dynamic shaper. And well, as Mauricio commented before, processing of those nickel-based superalloys, such as the CM247 and Inconel 713 low carbon, is not possible with powder bed fusion laser beam melting processes, because these systems normally work at room temperature, or we can nowadays find PBF systems that can preheat up to low temperatures as 400 or 500 degrees C. And so these hot cooling rates leads to hot cracking while processing the materials. And so the idea of Custodian was to tailor the beam shape to perform this preheating and postheating during the process, right? As I said, and as shown below before, we have two materials and we have 6 static configurations. We have six optics, which combines different primary and secondary beams. And for each optics, for each of the optics, we did a design of experiments to find out ideal conditions, let's say, where these materials can be processed, right? So from now on, we will see some samples, and I just wanted to remark that this is a common strategy for all the tests that we did. Basically, we set up to 9 coupons arranged in a square like this, and then we set 2 parameters that will vary in this design of experiments. In this case, for instance, is the scanning speed and the line offset, which is the separation between scan tracks, right? And for the rest of the parameters, they remain fixed during the process, so that we can analyze the behavior or what is the impact of these variables during the processing of these materials. And for all the experiments, we followed a 67 angled strategy between layers. So it means that scan tracks are rotated 67 degrees each layer, and a bidirectional approach. Okay. This is the mapping that we did for the multistatic beam shaper. So for each optic, we tested different parameters. Konstantin showed before that each optic has an optimized laser power, and this was something that has been modified because we found plenty of problems during the development. And as you can see in these images, what we obtained was a very huge balling issue, especially in the contours of the parts. And of course, if we reduce the energy density, as you can see here, by increasing the scanning speed, we also get this balling issue in the hatch because there is not enough energy. So here I just wanted to show you some other experiments with different optics. But all in all, what we concluded from these experiments is that the secondary beam is delivering so much energy that the powder is being partially melting layer by layer, creating these balls, because the powder itself is not conductive. So it absorbs all the energy, and then it becomes this balling shape that you can see, which is very remarkable, especially in the contours, because in this place the powder is not being melted, right? But heated by the secondary beam. Here I just wanted to show you some captures that we did in one of the experiments, so you can see the incandescent balls just after the melting of this coupon. And it's very problematic because it damaged the swiper, it damaged the powder delivery system, and so we cannot produce parts in a repetitive manner layer by layer, right? So with the dynamic shaper, the plan was to find a balance between the primary and the secondary beam, so that hopefully we should be able to find this processing window in the point where the primary beam is able to melt, has enough energy to melt, but the secondary beam does not create this balling issue, right? So that's why the dynamic MPLC was focused on playing with the power ratio between the primary and the secondary beam. Again, a Gaussian distribution from the primary, top hat for the secondary, and we have this range of voltage that we can adjust in the piezoelectric, in the galvo mirrors, so that depending on this value, we can obtain a power distribution between the primary and secondary beam, as you can see on the table. We can play from 50-50 to 23-77 for the secondary beam. Okay. And I will not spend so much time here. This is just for you to know that we carried out a huge process parameter mapping for both materials. So on the top side, you can see the experiments carried out for the Inconel 713, and as you can see here, we tested the whole range of the dynamic shaper. So from 1.7, where the primary beam receives more energy and the secondary beam has a limited energy, let's say, and up to 2.7 volts, where we have a power distribution of 2277. So the secondary beam has more energy in this case. And on the bottom, you can see the same for the CM247 low carbon. So we have followed different approaches. In the case of the Inconel 713, we have played with very low powers, as you can see here, 200 watts, 400 watts. We have increased the laser power slightly when using these other configurations because the primary beam has less energy. But in general, we used very low powers and very low scanning speeds, as you can see here, from 100 to 100. So these are very low scanning speeds for the PBF process. Meanwhile, in the CM247 low carbon, we played with just the opposite. So very high power. The limit of this optic is about 2 kilowatts. So we played with very high power, but again, on very, very high scanning speed. And that's because we wanted to map what is happening in different ranges. We have a limited time and we have two materials to produce, and so our idea was to go on with different approaches depending on the material. So all in all, you can see here that the green squares means that we got samples from these conditions, whereas the orange samples highlighted means that this coupon had to be stopped during the process because of building issues, right?
Last minute, Mario.
We can clearly see that when increasing the energy of the secondary beam, this surface roughness is heavier because it is creating this balling issue in the contours. This phenomenon is clearly observed in these images when varying the voltage of the galvo mirrors. All in all, I will try to speed up my speech. We selected some of the most promising shapes regarding the Inconel 713. CM247 is being characterized right now, but what we can see here is the sample 3/3 on the left present evident cracks, especially on the bottom and on the top part, while fairly sound structure is observed at the mid thickness. Cracks show features of intergranular hot tears, which are already observed in alloys produced by standard powder bed fusion systems. And on the other hand, sample 3/7 was selected just for the sake of comparison, because it, as you can see, it presents a huge amount of cracks and lack of fusion. If we look at the samples of experimental 4, which have a slight increase in the energy density, if I remember well, laser power was adjusted, was increased. Cracks at the mid thickness are significantly smaller, and large cracks with open faces are less frequent. So these features are similar to those of liquation cracks, where small volumes of low melting faces segregated at boundary shift to liquid during the process and reduce cohesion of the solid volume. So what we can conclude from this first assessment of the process is that the beam shaping induces a clear change in the solidification condition, leading to a remarkable improvement in the same quality. So especially if we focus on the mid thickness area, we observe that there are processing conditions where hot cracking is dramatically reduced, which is a good news. There is an evidence for some specific conditions that large hot tears can be almost fully eliminated. So in some cases, these cracks are replaced by smaller liquation cracks, which are related to the melting of constituents segregated at grain boundaries in the solid materials layers immediately beneath the laser tracks being processed. So all in all, there is a clear improvement of the process, but as you can see, further processing conditions optimization is required to achieve better results. That's all from my side. Many thanks for your attention. If you have any question, we will be pleased to help you at the end of the meeting. Thank you.
Okay, Mario, thank you very much for the complete explanation and well, all the images about the prototype and this whole overview. It was very, very interesting. And let's go now with the last presentation about the inline control system. It will be made by Roberto Fernandez from IMEN. Roberto.
Hi. Let me start.
Okay. Just tell me if you need something to share your presentation. Okay.
You can see, no?
Perfect.
Okay.
Go to the full screen. Right.
Okay.
Thank you.
So my name is Roberto Fernandez. I come from IMEN Technology Center, and this presentation was done together with Germán Vergara from NIT, New Infrared Technologies. And in the project, NIT was involved in the sensor part for the monitoring and control system for custodian, and IMEN was involved more in the development of feature extraction for monitoring and control of the process with the information from the sensor. Unfortunately, Germán cannot attend today, so I will be doing his part regarding the sensor technology. I hope I can do it well. So Let's start. This is the outline of the presentation. First, I will introduce the type of infrared sensors that we are using and why we are using this type of technology. Then I will explain how we used this technology to develop the custodian real-time process monitoring and control system. And finally, I will comment on how we are applying this technology in the powder bed fusion use case, which is one of the two use cases that we are applying this technology for in custodian. We are also applying it to laser beam welding. So why to use infrared imaging? This is because laser processes are processes that apply a lot of energy to the material, and they make big thermal gradients in the process and in the materials, and these energy gradients are the thermal process that the material is suffering. So it gives us a lot of information from the process and how it's behaving, and infrared technology is able to get this thermal information out of the process, as we will see later. And nowadays there are very fast infrared sensors on the market, so we can cope with the high-speed dynamics of the laser-based processes like powder bed fusion. So you can see here different laser processes. They have time constants that are very high. For example, in powder bed fusion, we are reaching from 1 to 10 kilohertz in the dynamicity of the process, if we want to really monitor the higher dynamic components of for example, the fluid movement of the melt pool and so on. So this is another demonstration. This is that the infrared the thermal information gives us a lot of information about the process. In the left, we have different simulation carried out by Technical University of Vienna with different process parameters, and we can see that we obtain different melt pool shapes and intensities, and from this information we can infer some of the quality of the process. This is another experiment carried out together by IMEN Technology Center and NIT company. In this case, they wanted to compare the effectivity of a CMOS camera and middle wave infrared cameras to detect the thermal information or the relevant features for getting process information from the process. In this case, they mixed all the features, and using some statistical analysis about the correlations and so on, they ordered the different features from the sensors, and they found out that the 21st most important components or features extracted from the image were from the infrared image, and only the 21th in the 21th feature we start to see the CMOS camera feature. So we have a little bit of a glimpse of how powerful the middle wave infrared cameras are in comparison with the CMOS normal sensors. And we use middle wave because after experimentation, it's found out that this is the range where most of laser process emit their light. This is another slide talking about the NIT technology. In infrared technology, we have basically two technologies, hybrid technologies. In this case, we have a detector array, which needs a hybridization process that connects it to the CMOS pixels, and you have to connect them pixel by pixel. So these hybrid technologies are very expensive sensors. And as we can see on the right, they can detect light in all of the infrared ranges, but they are very expensive. These cameras may cost around 50, 60,000 euros. And then we have the monolithic technologies. In this case, everything is done in the substrate of the initial CMOS wafer, adding some components to it, and this makes it more affordable. As we can see, NIT is working with this technology, which is the only one in the monolithic technologies which is able to give us information in the middle wave infrared range. Moreover, this detector from it is uncooled, so this makes the cameras much more simpler and reliable. And these two conditions, reliability and reduced cost, are the two main important to select this technology, because we are applying it for industrial applications. If it's not reliable or if it's very expensive, the industry is not going to adopt this for the everyday work. Finally, just another comment from NIT company. They are a very vertical company. They work directly with the silicon wafers, adding the additives for having the for manufacturing the middle wave infrared detectors. They also integrate the electronics around them, and they provide sensor boards and also camera boards to other people to integrate in their products. And finally, they also have different final products with where the hardware and software is ready out of the box to install in industrial facilities. So how we apply this NIT technology to the custodian project? We mix the NIT infrared sensor board together with an FPGA SoC board. This type of board combines in a single chip an FPGA, which is a reconfigurable logic that we can do any type of digital circuit in it, and a CPU or just a regular processor, where we can build very easily communications and another type of software. In custodian, we are observing the process using the middle wave infrared sensor, and then this enters directly to the FPGA, where we have custom FPGA blocks that acquire the image, process the image, and make some feature extraction from the image. These features and also the images are sent to the CPU memory. And the features are used by the controller to provide the control variables for the actuators. And also, we send the image and the features to some remote computer for visualization and capture. The control variables, in this case, in custodian, are two. We have the dynamic MPLC connected via Ethernet, where we can modify the galvo mirror voltage, and this is going to change the shape of the beam, laser beam. And then we also have it connected to the with an analog signal to the laser source, where we can modify the power and affect the process. And this is how the control loop is closed. So this is how the image that enters into the FPGA, and this is a 3D view of it. And then we apply some image processing to soften and clean the image, the noise, and so on. We also segmentate the image, generating this binary image from the mempool. And using these two images, we extract a lot of geometrical features from the mempool. For example, we can measure the mempool length and width, mempool area, mempool maximum level. We can measure lateral and frontal profile areas, and then we also measure the horizontal heating and cooling rates, which are important to observe the thermal process that the material is receiving. This is the final prototype that was built. In this case, we put a 64 by 64 sensor by nit, 64 by 64 pixels. There were bigger sensors available, but they are slower. So as a trade-off in between speed and spatial resolution, we opt for this sensor. And the system also has the Ethernet output, the analog output, and some digital inputs and outputs to interconnect with other industrial components to synchronize. How we apply this technology for the powder bed fusion. So as Mario was commenting, the first step was to connect the monitoring and control system to the PBF machine. In this case, we opt by an on-axis configuration. So the laser enters into the system, crosses several mirrors, and arrives at the process. And then the image from the process comes back all the way back to the monitoring and control system. So we always have a centered image with all the mempool in the image, and we optimize the spatial resolution of the sensor. These are some images that some examples of images we obtain. We see how we can see where the main spot is located, and we see always some kind of mempool or tail from the process. We can also visualize a hotspot or projections from the process using the camera. As we can see, we have enough spatial resolution even to try to measure the cooling rates from the process. This is a temporal analysis of the process. As we can see, while the layers are growing, the heat gets accumulated, and the part, because depending on the geometry, is not able to evacuate the heat as fast as in the first layers. So the heat gets accumulated. We can see this in the different images, and we also can observe it in the different features. We can have here a collection of different features during these 20 layers, and we can see that some of them are very good to measure the heat accumulation. For example, the mempool width, mempool area, and also the mempool maximum value and the profile areas are also good, measuring the accumulated heat in the process. So since the image in the PBF process is continuously changing from one side to another, left and right, and sometimes doing the borders, it's more difficult than in laser beam welding, where we have more stable mempool. it's very difficult to obtain clean features and accurate features from the geometrical features initially defined. So we obtain very noisy features, but we still can see the trend of these features. So in order to being able to monitor some variables in PBF application, we opted by using a per layer strategy instead of measuring instantaneous values of each feature, just averaging on a per layer basis the value of the different features, and we only apply the control in this moment. When some layer ends, we calculate the average value of the feature during this layer, and we apply the control, or if we want, in this moment. So in this sense, we can see that we can better, for example, now see the trend of the different features. It grows a lot at the beginning, and then in the middle, we don't know, it goes a little bit down and then goes up again. So in this sense, we can measure the accumulation of heat in the process. We wanted to apply this to avoid overheat of the process, and during this process, sometimes some person has to be watching the process to avoid overheat. In this way, we want to apply a control so we can make this control that the human is doing be made by the controller, no? Limiting the power being applied. So during these days, we are exactly doing that. What we are doing is defining a reference for the appropriate level of the heat during every layer, and we do so by averaging the first layers. So, and then we extract the average value of the first layers, and this is defined as the reference for the control after it. And then the controller goes modifying the power, reducing the power to avoid the overheat of the process and enable a construction of the part with more stable parameters. So this is a work that we are currently working on now. It's not finished yet. In this test that we did here, after the 8th track, the control enters, and in this case, there is a big difference here between the reference and the next layer value, so it goes totally down. But in fact, it works because it stops the feature from going up like in the other tests. So nowadays we are working on tuning the controller constants to have a more continuous control. So this is all from me. As a summary, in Custodian, we try to advance in the adoption of vision shaping technology for relevant industrial applications. And in these applications, it's demanded also for real-time monitoring and control system to be able to cope with the perturbations in the process that applies in a real scenario. So that's why NIT and IMEN developed together this monitoring and control system. We successfully applied it to laser beam welding. Now we are applying it for heat accumulation control in the PBF process, but it can be also applied to a different laser process because it's very flexible. We have a lot of features that are appropriate for monitoring different aspects of a process. So that's all from my side. Now, if you have questions.
Okay, Roberto, thank you very much for your presentation. And well, it looks like we are running a little tight on time. but we can have time for quick final questions. We have one question from Gabel asking, what are the main lessons learned applying the new methodology to PBF? I don't know if Mario or Mauricio or Constantine maybe, or you, Roberto, could give your opinion about the main lesson learned, or maybe Daniel, in this case, in the PBF process.
I think Mario could provide some words.
Yeah.
In fact, he in his presentation he has some results that well, the good thing is that we are reducing the quantity of cracks, but we still need to do more tests in order to make a final approach to at least to say if we will be possible to remove cracks completely. So I don't know, Mario.
Yes, well, in fact, it has been demonstrated that we don't have removed the cracks, but we have changed the type of cracks that we have.
Yeah.
That's one thing, and I think that is not only related to the outcome of the test that we did, but to the whole methodology. I mean, a lot of developments have been done for the from the point of view of the simulation, which is very complex. And this methodology can be applied not only for these materials that we are working, but we can find new applications that require tailored beam shapes that require this methodology to be applied. At the beginning, we didn't thought about the low conductivity of the powder and this balling issue that we faced with the multi-static beam shaper, but it's something that has been minimized with the dynamic shaper. And yeah, all in all, I think that this every step of this methodology has been a lesson from the point of view of new developments. And yes, as Daniel said, the things that we have presented is the current status, but of course it requires further tests to finally get rid of these cracks that we still see.
Okay, thank you, Mario. We have another question from Jose Juan. He says, great work. Just wondering how to calibrate the emissivity in the IR imaging. Most materials might change with temperature. I don't know who could respond, Mauricio maybe, or...
Regarding the camera, we don't measure the temperature. I don't know if this is the question, but we just calibrate it on an experimental basis for specific conditions of these tests. Okay. So for example, we do test changing speeds or other process parameters, and then we adapt, for example, the ranges in control. We find the correct value of the feature, and then we set the reference for controlling this correct value. But we do it experimentally. And yes, the question is correct. You cannot measure with a... I'm not an expert, but in IMEN they say that you cannot measure the temperature with a monochrome sensor. Maybe you have to go with some hyperspectral camera or something like that. Yeah. Okay. I don't know if... Okay.
Yeah, he says many thanks. It was responded. And there are no more questions. Then before finishing the webinar, just to tell you that tomorrow we have the final workshop, and I would like to encourage you to attend, because we will have not only the explanation about the project and the MPLC technology, but from Aymen and Marelli, they will make an explanation about a laser beam welding use case. And after that, we will have GFM and IDIME talking about the PBF laser beam in metal use case. Then finally, from Precitech, they will talk us about a use case also about laser cutting, then I think that the workshop will be really interesting. It's all on my side. I don't know, Daniel or the others, if you have any other things to say.
Oh, just to thank you to you all for your attention. So hope to see you tomorrow in this more industrial-oriented workshop. So in which you can see from the end user's perspective what we have done in custodian, particularly for PBF and LBW, and also cutting. But initially, just 2 end users were presented in the consortium for the 2 first applications. The cutting issue was implemented during the project, and Presitech will be in charge for that. But anyway, thank you to you all for joining us today on keep in contact. If you have any question or possible doubt, don't hesitate to contact us. And always you can check our website, yourlaser.eu, in which you can find more additional info.
Okay.
So, thank you very much.
Thank you very much to you all.
Bye. Bye.
See you tomorrow in the workshop at 3 p.m. Thank you.
Bye-bye.
See you.
Hey, jefa, que te has quedado sola aquí. No sé si em sents. La única que no estava atenta. No!